Einstein's theory feels untouchable, elegant, final. We are taught that it revealed the true structure of reality and closed the book on space and time. But physics itself tells a quieter, more unsettling story. Einstein's theory is not complete, and the people who work with it every day know it. We live as if space-time is a solved problem, as if gravity has been fully understood, as if the universe finally makes sense at its deepest level. This belief is comforting because it gives us a foundation, something solid beneath everything else. But in physics, comfort is not evidence. The moment you look closely, the cracks appear. Not because Einstein was careless or wrong, but because reality refuses to fit inside any single model. Einstein gave us a description of gravity that changed everything. Space and time were no longer a stage. They became part of the drama. Matter told space-time how to curve, and curved space-time told matter how to move. This idea worked spectacularly well. It predicted black holes. It predicted gravitational waves. It explained why time slows down near massive objects, and why clocks tick differently depending on where they are. From the outside, it looks complete, but completeness in physics is not about success. It is about scope, and scope is where the problem begins. Einstein's theory describes gravity as geometry. It works when space-time behaves smoothly, continuously, predictably. But the universe does not always behave that way. At the smallest scales, reality becomes granular, probabilistic, unstable. Quantum mechanics dominates. And here's the first uncomfortable truth. Einstein's theory does not know how to speak the language of the quantum. It cannot describe space-time when space-time itself fluctuates. It cannot tell you what happens when curvature becomes infinite. It cannot explain what space-time is made of. It treats space-time as fundamental, even though everything else in physics stopped being fundamental decades ago. This creates a strange tension. On one side, we have quantum mechanics, which governs particles, fields, and interactions with extraordinary precision. On the other, we have general relativity, which governs gravity and space-time with equal precision at large scales. Both theories work. Both are correct where they apply. And yet, they cannot be combined. When you try to use them together, the equations break. The predictions become meaningless. Infinity appears. And infinity, in physics, is a confession of ignorance. Think about black holes. According to Einstein's equations, collapse matter far enough and space-time curves endlessly, forming a singularity. A point where density becomes infinite and the laws of physics stop working. That is not a solution. That is a warning sign. Nature does not produce infinities. Infinities appear when a theory is being pushed beyond its limits. The singularity is not telling us that reality contains an infinite point. It is telling us that Einstein's theory has reached the edge of what it can describe. The same thing happens at the beginning of the universe. Run Einstein's equations backward and you reach the Big Bang singularity. Again, infinity. Again, breakdown. Again, silence. The theory gives up, and physics admits this openly. We do not know what space-time is doing at those extremes. We do not know what gravity becomes when it meets quantum uncertainty. We do not know what the universe was like before classical space-time emerged. These are not fringe questions. They sit at the center of modern physics. And the unsettling part is not that we lack answers. It is that Einstein's framework cannot even ask the right questions. This leads to a deeper realization. Einstein's theory may be emergent, not fundamental. Just as temperature emerges from the motion of particles, space-time curvature may emerge from deeper microscopic processes. If that is true, then space-time is not the bedrock of reality. It is a surface phenomenon, a large-scale behavior that hides an underlying structure we do not yet understand. Many approaches to quantum gravity point in this direction. Some suggest space-time is built from discrete units. Others suggest it emerges from entanglement. Others propose that geometry itself arises from information. These ideas differ wildly, but they share one implication. Space-time, as Einstein described it, is not the final layer. It is an approximation, extremely accurate, profoundly useful, but incomplete. This is where intuition fails us. We tend to think that a theory is either right or wrong. In physics, theories are more like maps. A map can be accurate without being complete. A map can guide you across a city while telling you nothing about what lies underground. Einstein gave us a map of gravity that works beautifully across vast distances and times. But maps do not tell you what the paper is made of. And when you reach the edge of the map, you do not fall off reality. You simply run out of guidance. The danger is not that Einstein's theory fails. The danger is assuming that because it works so well, it must be fundamental. That assumption shapes how we think about reality itself. It encourages the belief that space-time is the ultimate container of existence, that geometry is the final answer, But physics keeps pushing back. At the quantum level, locality breaks down. Events do not have definite positions until measured. Entanglement links distant systems in ways space-time struggles to describe. Information behaves as if it is more basic than distance. These phenomena do not sit comfortably inside Einstein's universe. They suggest that what we experience as space and time might be a derived description, not a primary one. Here is where the illusion becomes personal. You experience the world as happening in space and time. Objects have positions, events have durations, causes come before effects. Your mind treats this structure as unavoidable, as obvious. But if space-time itself is emergent, then your experience is tuned to a layer of reality that is not fundamental. Your brain evolved to navigate an effective world, not the underlying one. It presents space-time as a given because that is what allows action and prediction. If the true structure beneath space-time operates differently, you would not feel that difference directly. You would only feel the layer you can interact with. This mirrors what happened with classical physics. For centuries, we believed space and time were absolute. Newton's framework felt complete. It worked. It explained motion, forces, trajectories. Then relativity showed that space and time themselves depend on motion and gravity. The foundation shifted, but everyday experience did not. Tables did not dissolve. People did not feel space-time bending. The interface stayed stable while the underlying description changed. The same thing may be happening again. Einstein replaced Newton. Something else may replace Einstein. And when it does, your experience of reality will not suddenly feel different. The rules you live by will still work locally. The interface will still function. But the story you tell about what reality is will quietly become obsolete. This is why physics admits incompleteness without panic. Scientists are not shocked by this situation. They expect it. Every successful theory eventually reveals its limits. What makes Einstein's case unsettling is how deeply his framework is woven into our understanding of existence. Space and time are not just scientific concepts, they are psychological ones. They shape identity, memory, causality, meaning. To admit that space-time is not fundamental is to admit that the stage on which life unfolds may itself be a construct, not an illusion, but a derived structure, real but not ultimate. So, what replaces it? No one knows. And that uncertainty is not a failure, it is a signal. Physics does not promise final answers. It promises increasingly accurate descriptions, each valid within a domain. Einstein gave us one of the greatest descriptions ever built, but the universe is under no obligation to fit entirely inside it. And here is the quiet conclusion that changes how you should hear the title. Einstein's theory isn't complete, does not mean reality is broken. It means reality is deeper than any single model. It means that what feels fundamental may be provisional. It means that the confidence you place in space-time as the ultimate backdrop of existence is a habit, not a proof. You are living inside a description that works remarkably well, while standing on a foundation that is still unknown. And when physics finally uncovers what lies beneath space-time, it will not feel like a revolution in daily life. It will feel like continuity. Because continuity is what the interface is designed to preserve. The deepest changes rarely announce themselves. They simply redefine what was always there. This is Veritas Labs, where truth is tested